science results that have been obtained by this very powerful instrument. What you have here is the delay lines. This is again a big thing. We consider it part of the telescope system. We fit the beams, the light from 4 of our telescopes into these devices that run along these long rails. So the light is made to interfere. You need to do this in a very precise way. Remember that the wavelength of the near-infrared light is about a micron or 2, 1 or 2 microns. You need to have everything to a precision much better than 1 or 2 microns. And this has been a big challenge. It took about 10 years to develop this project, this infrastructure project, and the cost was about 100 million. But it's now working very, very nicely. It's basically pressing the button and it works. So amazing. And this one, it's gravity. This is one of the instruments that we have on this interferometer. That it's actually, again, another technological wonder. It has been produced by a consortium in the community led by the Max Planck Institute in Garching, and I will show you in a minute one of the most outstanding results that they have obtained with this beam combiner. So at this point you can imagine that one of the strengths of Paranal, of the VLT, is the variety of instruments we have. We have everything in there. We have spectrometers, we have images at all wavelengths. Each instrument is equipped with 3 instruments, plus the ones in the interferometer, plus another instrument called Espresso, which actually what it does is to just bring the light from the 4 big telescopes together into a single spectrograph, and that is equivalent to having 1 telescope of 16 meters in diameter. So really, really fantastic. And this is, it comes with where we would like to go in the next years. Some of the instruments will be retired. For example, this one has been retired a few weeks ago, actually. It's called NACA. It was the first instrument using adaptive optics at the VLT, and what you can see in this cartoon is just a little legacy of the fantastically sharp images that this instrument left, together with of course, a lot of other data. Maybe I should point out this one. This is the very first image of an exoplanet. This is a star, and this is a planet orbiting around it. It's very far, but it was really the first time that this was even possible. You can see Saturn here, and many, many other things that NACA has been able to study and left a gigantic legacy behind. I was talking about adaptive optics 1 moment ago. It really works very nicely. This is this is what we call adaptive optics in white. In the white field, you can see if you switch it off, you have this direct image from the sky. If you switch it on, you can really get a much sharper image. You can go down to typically 0.2, 0.3 arc seconds of PSF in here, but we have another mode which is concentrated on a very small part of the focal plane, where we can really do much, much better than this. This is actually Neptune, and this is a direct image of Neptune without any correction. When we switch on the adaptive optics facility, it produces an image like this one, that it's even better than the one from the Hubble Space Telescope. So this is really, really fantastic, what can be achieved with today's technology. I already explained a little bit this Espresso instrument, which combines the light from the 4 big telescopes into a single spectrometer. This is now fully commissioned, and it's ready, and the community is making use of it, both to find planets orbiting around other stars, but also trying to challenge the constancy of the fundamental numbers in physics, trying to see whether fundamental physics constants are the same today as they used to be in the very distant past. And here what we have, it's also the other novelty for the BLTI, which is called Matisse, and this is actually an imager in the mid-infrared at very high resolution because it uses the interferometer. Now, the secret of Paranal, the way it works, is that at ESO we build the telescopes, we build all the infrastructure that we all do ourselves, but the instruments we develop together with the community, with consortia of R&D institutes and universities in the community. We normally provide the capital spending on this, the money to pay for the hardware, and the consortia pay for the work, for the effort. Of course, this model has been changing a little bit, and then what we do, because the consortia put the money themselves or they get it funded from the national agencies, we reward them with guaranteed time observations. We grant observing nights to this consortia to do outstanding science. And when the instruments are delivered to us, we operate the whole thing. We operate the telescopes and the instruments. And one very important number that we want to keep at all times is the technical downtime being very, very small. At the moment, we are keeping it below 3%. Actually, last year I was looking at the numbers in Paranal. We were about at 2.5% of technical downtime. In La Silla, we are at 1% technical downtime. That means that when we have a night scheduled to do science observations, to do astronomical science observations, we don't lose time. We don't lose time because there are technical issues in there. So I believe this is a very valid model that we are now exporting to the EELT as well, to the Extremely Large Telescope. I think it's probably worth to mention today that this year the Nobel Prize in Physics was granted to astronomers. Half of it went to Michel Mayor and Didier Queloz for the discovery of the very first exoplanet around 51 Pegasus. And this is actually the light curve that they obtained. This is the principle of this is that you don't see the planet orbiting the star because it's too faint or the star is too bright, but what you can actually measure is the motion of the star going back and forth because there's a planet orbiting around it. Of course, the bigger the planet, the easier it is to detect it through this way. And this is why the very first exoplanet that was discovered has a mass of about 8 Jupiter masses. So it was a really big one, very close to the star, but this opened the way to the discovery of more than 4,000 exoplanets as we know today. So Michel Mayor and Didier Queloz were awarded this Nobel Prize because they discovered the first one, but of course they discovered many, many more, and a big deal of them in this telescope, in the 3.6 telescope that we have in La Silla, with an instrument that Michel developed himself with his team, which is called HARPS, and that's actually something that we need to thank him very, very much for having allowed so many discoveries in our telescopes. Here's another interesting exoplanet discovery from 2016. Again, this is a radial velocity curve. This is the motion of the star around which there is a planet orbiting, but this is the nearest star to the Sun. This is Proxima Centauri, and it is remarkable that around Proxima Centauri there is a planet already orbiting. Even more, it's an Earth-like planet. It's only 1.3 times the mass of the Earth. Of course, Proxima, it's very red, very low mass, so this planet is very close to the star, and the period is only 11 days, which makes our life easier. And as you can see, it's very, very close to the star. Now, there's been a lot of speculation about whether this planet could be habitable or not. Maybe the surface temperature of this planet would allow for water to be liquid if there is any water there, but there's a number of other issues, like the fact that Proxima Cen is very active. It produces a lot of cosmic particles, and it would be very difficult to sustain any type of life in there. But okay, it's still interesting that first star we look at towards the outside of the solar system, there is a planet very similar to the Earth, actually. So that probably means that there's lots of them to look for in the galaxy. That's another interesting system. This is called Trappist 1. Trappist did a small telescope that was placed in La Silla by a team led by Belgian astronomers. If there's any Belgian in the audience, you know that Trappist is a beer. They observed this star, TRAPPIST-1, which is rather red, for a long time, and they found 7 planets transiting in front of the star. And they are all about the size of the Earth, and probably those 3 are in the habitable zone, meaning that if there is water in the surface, it will be liquid because of the surface temperature. And the way these discoveries are made is looking at these transits. When the planet goes in front of the star dims a little bit, and if you have sensitive enough telescopes and instruments, you can actually measure this. And, run out of batteries, good, no problem, no. So you can measure this dimming here, and from this you can infer the size of the planet. And this one, it's very interesting. This is obtained with the VLT, with a very large telescope. You can see 3 planets transiting in front of that star during the same period. So this is really a very nice result, which is also telling us something else, that maybe there's a lot of multiple planet systems around the galaxy. So there's a lot to explore in that field. That was another important discovery that, where everyone contributed, but also ESO. This was the very first gravitational wave event that was long enough to be followed by optical facilities or by ground-based facilities. It happened in August 2017, and ESO spent about 150 hours of observing time, putting almost every telescope to do something about it. We know today that this was the coalescence of 2 neutron stars, and one of the key observations was this one that was actually led by Elena Pian. This is the lag time since the gravitational wave event came in days, so that was taken 1.5 days after until 10.5 days after. And you can see that at the start this is very much a black body, and then you start seeing all the features, all the atomic features of very heavy materials that have been produced during this neutron star merger. So that sequence of observations was actually key to establish the nature of this gravitational wave event, which was the first one that we could, as I say, follow up from the ground. Now this is another very nice one. This is with gravity, with this instrument on the interferometer. So this relates to the supermassive black hole that we have in the center of our galaxy. It has a mass of 4 million times the mass of the Sun, and there is a star orbiting it that, okay, let's see if I can make this work, because I can see it. So, oh God, I can see the arrow. Okay, good. So there's a star orbiting this black hole every 16 years, and in May 2018 it got so close to the black hole that the speed of the star was about 1% of the speed of light. Very, very close, where you can expect to feel strong gravity effects as the ones predicted by general relativity. And what the team did was to measure the position of the star very accurately to an accuracy of a few milli-arc seconds, and the velocity of the star. And when you plot the velocity against the position, this dotted line is what Newtonian gravity, what Newton's law would predict for the velocity, and the red line is what general relativity would predict. And as you can see, the measurements follow very closely the prediction of general relativity. So that was really a fantastic measurement confirming general relativity. Of course, if they had found that general relativity was wrong, they probably would have gotten the Nobel Prize by now, but it's okay. It's also good sometimes to learn that we're having the right assumptions. Okay, let's see if I can move to the next one. No. Yes, this is also with the same instrument. For those of you who are lovers of active galactic nuclei, those are supermassive black holes, much bigger than those in our galaxy, with a lot of material falling into that supermassive black hole. And this is the explanation of why quasars that were discovered. The first one was this one, 3C273, it was discovered in 1973, why quasars shine so much, why they emit so much light. And here the measurement was that actually with this instrument, with gravity, they could see the gas rotating around the supermassive black hole. So this is something that we also had been assuming for some time, and that it could only be measured directly with gravity. So you can see the gas here coming towards us. This is the radio axis. This is what we understand. It's the rotation of the whole thing, and the gas at this other side, you see it going away from us. So there's evidence that this is rotating. Now, for those of you who are studying astrophysics now, your teachers and professors will tell you that stars are point-like in the sky. That was true until a few years ago, where we were able to resolve red giants like this one. This is a star. It's called Pi 1 Grus. And thanks to the interferometer, a team led by Claudia Palladini, who's one of our staff astronomers, they could actually obtain this image of the star and resolve it. So the star is no longer a point, and you can see these convection cells. This is a giant star. You expect convection to be driving transport from the inner parts of the star to the outer part. And this is really a beautiful image where you can see these convection cells, the same that you can see them in the boiling pot of water when you put them in the kitchen. So that's really also a groundbreaking discovery. Okay, I don't think I have time to go into apex, just to leave you with this statistics on Paranal, on the VLT and the VLTI. We observe about 160 nights per semester, so this is really a lot of time, and this is one of the key reasons why ESO is so efficient in delivering good quality and good quantity of data to our astronomers in the member states. Of course, this is complemented by a lot of work that we also put into the archive. All the data are archived. We have quite advanced archive products to grab the data, to work with them, and we are also renewing the proposal system and installing a data flow system that goes all the way from when the astronomers request observing time to the data that you can find in the archive maybe 2 years later. And we're putting also a lot of effort into this. And this is just an example on how the archive looks like. You just type the coordinates. This is the galactic center. As you can imagine, there's zillions of observations in the galactic center, and you can click in any one of them, and you download the data and see any associated data products. Okay, let me speak a little bit about ALMA now. ALMA is a different type of beast. It's the largest by far millimeter and submillimeter radio interferometer. It is not an ESO-only program. It is partnership with the National Science Foundation in the United States and with the National Institute of Natural Science in Japan. The observatory itself is placed in here in the Chagnator Plateau at 5,050 meters, rather hostile environment. There's not very much air in there, so we go there as little as possible. There's 66 antennas that can be moved into about 190 positions in this 16-kilometer plateau in there, and we also have in this in the building, if I have a picture in there, yeah, there's this technical facility building here which contains the clock and the correlator, which is a gigantic supercomputer that deals with the signal, with the digitized signal of all the 66 antennas and builds the interference patterns with them. This is actually a picture of the correlator at 5,000 meters altitude. These antennas, as I mentioned, they can be moved from one place to another to have different configurations, more compact to cover a wider field of view, more extended to cover less field of view, but with a higher resolution. And this is actually a 360 image of the control room, that it's not at 5,000 meters, but where the base camp for the operation center is at 3,000 meters. And this is, well, I mean, this is the place where the astronomers and the engineers live when they are there. So ALMA has been working, it started operations in 2011. I believe that we can finally claim that we are now in steady state. Basically, all the modes are commissioned, they are all available, and there's lots of science coming out. And we're now in cycle 7. There's a cycle every year. There's a call for proposals, a selection process, which is very tough. This last time we received almost 800 proposals from all over the world. ESO gets about 34% of the observing time, and still our community, our very active community, they put something like 41% of the proposals. So we are the largest generators of frustration in Europe, because we have the highest oversubscription factor. Of course, our people, our astronomers in Europe are so engaged that their proposals are so good that 40% of the refereed papers coming out from ALMA come from European astronomers, which is really very, very good. But of course, it puts a lot of pressure on us to deliver very good data. There's a development plan for ALMA that's included in the budget, and we're working together with our partners to have, hopefully, to increase the sensitivity and be able to multiply it by a factor of 2 or so. And just here you have a couple of results. This is actually a galaxy cluster. This is a combination of X-ray data and ALMA data and VLT data, where this jets, which is the red thing, this is what ALMA reveals. And this is a very high redshift galaxy. This is actually an oxygen 3 emission line, not the optical one, but one that comes up at the millimeter band at this redshift. Very high redshift galaxy that ALMA can identify very nicely. This is one of the large projects that has been done with ALMA, and this is a mapping of a number of protoplanetary disks around young stars, where you can see all these rings, these rings in here. Those were predicted long time ago when ALMA was being built, when ALMA was being considered, because the astronomers thought that this would be the way that planets form. Planets would be formed in these empty rings, in these debris disks, in this planetary stuff that surrounds the stars. And we're now seeing evidence of this. We see that most of these young stars actually display these rings around the planetary star. In some cases, we can even find that those rings are resonant and caused by a planet. It's tough to see it, but it all fits if you model it as being caused by a planet. So this is really, really a beautiful outcome of ALMA that was, as I say, predicted before ALMA was even built. And of course, this is the result of 2019, I would say, which is the shadow of a supermassive black hole of 6,500 million solar masses black hole at the center of this active galaxy of M87. This was achieved by an international consortium called Event Horizon Telescope that used 7 millimeter radio telescopes around the world, including ALMA and APEX, which are the ones that ESO is participating in. And what you see here, it's actually the orbits of the photons, of the millimeter wave photons. It's not the innermost stable orbit, actually. This is not matter, this is light orbiting around the black hole. Gravity is so strong that photons follow an orbit around it. And it perfectly matches with the expectations. This shadow, it's about twice larger than the solar system, which it fits exactly with the size of a black hole of that mass. And I like to show this thing very often, as much as I can, because this is how the image of the black hole would have looked like without ESO. So I think we made a substantial contribution to this thing looking as a black hole. Of course, there's a lot of things. There's almost 10 papers now with interpretation of this data. There's a lot to work on, you know, what are these things? Are we seeing the base of the jet here? What are we seeing? There's lots of ongoing work, but the fundamental thing here for me was to see that the way that I had been imagining a black hole in my life, it appears to be more or less okay, which is very pleasant. Okay, ELT, the Extremely Large Telescope. This is still Photoshop, but starting from next slide, there's no more any Photoshop. So the ELT, it will be the largest optical infrared telescope in the world. You will hear the same thing from other telescopes led by the US, which of course are not going to be the largest ones, but fine, they are in the US. This one will have a primary mirror of almost 40 meters across, and the mirror is segmented. It's not made of one piece. It has the same basic technology as the Gran Tecan, the telescope in La Palma, which has 10.4 meters across, and it's made of 36 segments, each one of them 1.4, 1.5 meters across. The ELT uses the same size for the segments, but instead of 36, it will have 800. So it's really a gigantic step forward. And don't forget that the Gran Tecan today, it's the largest optical telescope in the world. So we're building something that will be a number of times much bigger than the largest telescope that we currently have. Actually, in terms of collecting area, it's about 14 times bigger. In terms of angular resolution, using adaptive optics, it will be 4 times better. And combining the two, it gives, you know, breathtaking amplification factors. Construction started in 2015. We expect to achieve first technical light 2025. Funding is provided by the ESO member states, and we will place it in Cerro Armazones, very close to Paranal. So this is the telescopes that we have today, the KEX. This is the 4 VLTs, the Subaru, Gemini North, Gemini South, and this is the GTC, the Gran Tecan, and this will be the ELT. So the ELT will have a larger collecting area than all of the others put together. So that's really a very important step forward. As I mentioned, the ELT will be placed in Cerro Armazones. This is a mountain about 3,000 meters of altitude. It's only 20 kilometers on a straight line from Paranal, where the VLT is. We have a road that we have built to get there, and it takes about 40 minutes to get from one point to another, which means that we will do all the operation from here, from Paranal. So science operations will be done from here. We will take advantage of all the facilities that we have at the site. I hope I can show you a little movie here. This is how the top of Armazones looked 3 weeks ago, I believe. So what you're seeing now is the inner part where the telescope will be sitting. This circle has 55 meters in diameter, and it's 7 meters in depth for the foundations. And what you can see around it, it's where the dome in here and the auxiliary building in there will be sitting. Diameter of this thing from here to there, it's about 110 meters. The dome will be almost 70 meters high. And yeah, I mean, it's quite scary. I mean, this platform is not very big, so when you will be watching from here, you will see the dome going up there. So it will cover very much everything that you have in front of you. And we're making very good progress at the moment with this, and in a few months we will start putting walls here in the auxiliary building. The telescope itself, it will weigh about 3,600 tons, out of which 2,000 are in the structure, in the steel structure. Then, of course, we have the mirrors and all the electronics and all the actuators, which also carry a lot of mass. So it's quite a scary beast, to say the least. As I said, we will operate this from Paranal, where the VLT is. This is the VLT, the Very Large Telescope base camp. And this building here that we're about to receive now, this is the ELT technical facility. This is where we will be washing, stripping, and aluminizing the mirrors of the ELT. fixing the technical issues. So as I said, the same engineering team that will do the maintenance of the ELT, it's the one that is doing the maintenance of the ELT. Of course, we need more people, but okay. I mean, we're not building a separate observatory. And as I said before, we've spent a lot of time doing reviews and design and things like that. We're now down to earth with the work. There's this actual hardware being produced, and you can see some of it here. I mean, this is the first batch of the mirrors of the glass, of the mirror segments on the primary mirror. There's 18 of those now that have been delivered to the polisher. This is the M2, the secondary mirror that will be hanging at an altitude of more than 60 meters. It's a 4-meter diameter mirror, and it's being polished, as you can see here. This is some actuators that go below the mirror segments of the primary to make sure that the mirror it keeps its shape. And this is actually in a test bench that we have in Garching in our headquarters. Those are pieces of the dome that are already being fabricated, and this is actually the earthquake dampers that will go, that are being actually put into all the structure of the telescope. So all this is now going at full throttle. Of course, we're encountering problems now and then, but I think we're now at full speed with the project. So the day one instruments that we will have, actually the first light instruments will be those two, Mikado and Harmony. Mikado, it's a camera, it's a high resolution camera with a pixel size of 4 milliarcseconds. It will be fed by an adaptive optics device, which is called Maori, which is actually LED here in Bologna. It's a bit late, and we're actually still struggling a little bit with the design. Mikado will have a facility called single conjugate adaptive optics that can work for a couple of years or so, but ultimately it will have to be fed by this full adaptive optics module. Then Harmony, it's an integral field unit, again something that produces tomography. It gives you an image with a spectrum for every pixel. This is being developed by a consortium led by the University of Oxford. And METIS, it's a mid-infrared instrument offering multiple capabilities like imaging, spectroscopy, and polarimetry. Those are the first instruments. Those two will be hopefully first light. This one will come a bit later. And then for the more distant future, we also studying how to realize those two instruments. HIRES, it's very stable, high-resolution optical spectrometer, again to do radial velocities, much better than Espresso, etc. Mosaic, it's a multi-object spectrometer that will have a huge multiplexing factor led by France. And ultimately, in maybe 15 years, we hope that we will be able to develop an extreme adaptive optics instrument called PCS, that if there is solar type star with an Earth-like planet orbiting around it within a reasonable distance, we should be able to image that, to image the planet separately. That's really a very challenging thing to do, and there's a lot of R&D that we need to make progress on. So I think I need to skip all of this because I want to talk for a couple of minutes about CTA for very good reasons. As you know, the project office, it's here in Bologna across the road. So CTA, it's a very high energy gamma ray observatory in the ground. Of course, the atmosphere is opaque to gamma rays, but what happens when you have gamma rays with an energy of the order of a tera electron volt is that they disintegrate in the atmosphere. They produce an electron-positron pair with a lot of energy. Those further disintegrate into secondary particles, and at the end of the day, what we receive is a flash of blue light in the surface of the Earth. We can even compute the opening of these flashes because we know where these gamma rays disintegrate optimally, and we know all the basic physics that goes into it. So if we have a set of optical telescopes like these ones, being able to detect these flashes, which are really very, very short, we're talking nanoseconds of duration, we should be able to reconstruct the direction in which the gamma ray comes and also to measure its energy. Now, this is working. There's at least 3 of such devices around the world. There's one called HES in Namibia, there's another one called MAGIC in La Palma, and there's another one called Veritas in the US. So the basic concept works, but those 3 things are experiments. What CTA will be is an observatory. And an observatory means that it will be able to access a lot more sources and to do a lot more different types of research than just measuring one single thing. And it will be offered to the community for exploitation, very much as we do with ALMA or with the VLT. So what has ESO to do with CTA? We're not going to build it. The people across the road will do that, Federico and Wolfgang and the others. They will take care of the construction, but we will host CTA South and operate CTA South for CTA. Today it's a company, and it will become an ERIC, a sort of organizational setup under European Union law. So we signed all the agreements about 1 year ago. We are a partner of CTA, and actually 10% of the observing time will go to scientists from our member states. And we are now looking forward to the first steps to establish CTA South in Paranal. That's it will become part of our Paranal Observatory as well. Again, science operations done from Paranal, same maintenance team as for the VLT and the EELT, etc. And we really look forward to make more progress about this. Okay, I'm getting to the end now. This is just to say, if there's a key performance indicator on which I would like ESO to be measured, it's this one. It's the number of scientific results achieved using our facilities. And since a couple of years, we're now enabling more than 1,000 scientific papers with our observations, which I believe it's a very nice number. I also want to underline that more than 30% of these results use the archive, and actually half of them only use the archive. So they don't need new observations. They just go to the archive, dig on it, and find data to do science, which is good. That's why we also need to maintain our archive. And you can see in colors here, color-coded the contributions from the various instruments that we have. La Silla, the VLT, which is of course the main contributor, but also ALMA, and so on and so forth. So that's good, and this is what keeps us working. We're also doing a little bit of outreach effort here. We were happy that a philanthropist called Klaus Tschira, a German philanthropist, donated to us the money to build this facility that we call the ESO Supernova Planetarium and Visitor Center that we started operating last year in April. We've got more than 100,000 visitors coming, and more than 1,000 planetarium shows, more than 12,000 students engaged in educational activities. And those are not only Germans. I mean, there's lots of people from abroad coming. We even do teacher training courses, and the last group that we had was actually an Italian teacher group. So this is a facility that we really want all the member states to take advantage of. So if you are interested, this is really a beautiful facility. If you ever come to Munich, please don't miss to visit it, and you have the web page in there. Okay, so I couldn't miss to put this one from Marcella Brusa, which is the, this is the spectrum, well, this is the spectral energy distribution of NGC 6240, which is a starburst galaxy, very heavily obscured, with 2 massive black holes at the center of it. But instead of putting it where it is today, we put it at very high redshift, at redshift 7, virtually at the onset of galaxy formation. And you can see how all these facilities that ESO and ESA and other actors like SKA will bring in the 2030s, they will be able to feed the astronomers with all the data to analyze this type of sources. Very heavily obscured, very powerful AGNs at the very early epochs in the history of the universe. And Athena, of course, I had to mention. I couldn't miss that either. And now LISA as well as the Gravitational Wave Observatory that ESA is planning to fly around 2035. And of course, that will be able to detect supermassive black hole mergers, of which probably NGC 6240 will become one in a few years to come. Maybe in a few more than years, but okay. Right, as I say, I'm heading to the end. I hope I have convinced you that ESO has a very solid international standing at the moment. With the VLT and the VLTI, we are actually at the forefront of optical and near-infrared astronomy for a variety of reasons, for the number of instruments that we have, for the uniqueness of some of them, like the interferometer. With ALMA, we are also enabling a lot of science in Europe, also in the US, in Japan, together with our partners. You can see amazing results from ALMA almost every week. And the ELT, we're not only going to be the ones with the largest telescope, but it's the one that will come online first. The current schedule for the other two ELT projects, which are led in the US, the Giant Magellan Telescope, which is a 25-meter equivalent telescope, and the TMT, a 30-meter telescope. They project first light around 2030. They do have funding issues. I wouldn't say that we don't, but okay. But theirs are much, much bigger than ours. And now there's, of course, the decadal survey, the ASTRO 2020 decadal survey, that will evaluate whether the US, the United States government, wants to put some funding from public sources into these projects. The TMT, it's still not having a secure site. They wanted to go to Hawaii, to Mauna Kea, but there's serious issues there. They have a backup site in La Palma, but we'll see. I mean, they are in this difficult situation that I really don't envy them for it at all, and I really would like them to get out of it as soon as possible. So at ESO, with the full backing of the member states, we are online. We're on track for delivering the ELT with first technical light around 2025. So this is several years before our US competitors. So that situation was unthinkable only 10 years ago. Of course, at ESO, it took a long time to get this project started and secured, but then when we started, we're marching very solidly towards the future. In space, I would say we're also in a good situation. As you probably heard, there was an ESA ministerial conference 3 weeks ago in Seville, in Spain, and the ESA ministers approved an increase in 10% of the science budget for the next 3 years, which is very good. And we hope that this will enable these two big observatories, Athena, an X-ray observatory, and LISA, gravitational wave observatories, to fly around from 2030 to 2035. And that will be a very nice complement and open a number of synergies with the facilities that ESA will have at that point in time. JWST, the James Webb Space Telescope, which is sometimes called the successor of Hubble, although it operates in the near-infrared and the mid-infrared. The launch date is now 2021. It will probably be late 2021, but okay. There's plenty of opportunities for synergies as well. And I would say that, as I mentioned in the beginning, I'm very happy that we have very good cooperation with ESA on these activities, because ultimately we target very similar science goals and we work very often for the same community. Okay, so that was all. I'll leave you with the video while you put me some difficult questions. Thank you very much.
So, thank you, Xavier. So don't be shy, and if you have questions, curiosities, take the opportunity to have the ESO Director General here, live. Still.
shot, don't be shy.
A young student, Bruno. wait.
I can also speak loud. Has the Brexit process any influence on ESO activity, on ESO coordination?
So far not. The UK will continue being part of ESO, no matter whether they are part of the European Union or not. That doesn't make any difference. Of course, from the logistic points of view, it could make our life a little more difficult with the imports of the items that we procure in UK industry or with the instruments. I said that Harmony, which is first light ELT instrument, it's led by the University of Oxford. So that may come with a little bit of logistic challenges, but I hope it will not be a big deal. Yeah, for the time being, we seem to be okay.
Come on. So do you have any suggestion for students in their college courses here for their career?
Absolutely, yes. I mean, I never mentioned this, but at ESO we have a student program. At any point in time, we have about 40 students, either in Germany or in Chile. And the program that we have, we offer up to 2 years, from 1 to 2 years, to PhD students that are doing their PhD in universities in Europe. We offer them to be at ESO for 1 to 2 years. We assign them a co-supervisor, and then they go back to their institute, to their university, to get their degree. On top of this, at any point in time, we also have about 40 postdocs, 40 fellows. Fellowships are, they last typically 3 years in Germany, and in Chile we have a different arrangement whereby these people spend 3 years in Chile and then 1 year wherever they want, and we still pay them. So they can go back to their country or somewhere else. That's not a problem. And this is actually a very productive way of working for us, because when you look around many big institutes and astronomy departments around the world, not just in Europe, you can recognize in the directors of these places faces of people who were ESO fellows one day. So it is, for us, it's just a very good investment. So please do not hesitate and look at our recruitment pages, because there's good opportunities for people if you are interested in this. Johnny.
You mentioned 2025 for the first technical light.
Yes.
Does that mean that 2025 is also the time at which both Harmony and Mikado will be at the telescope? No.
No, 2025, not even the telescope will be complete. Mm-hmm. It will be 1/6 of the primary mirror only, and then we have a commissioning plan for the next year, more or less, or two, to put the telescope together and start commissioning the first light instrument. So, as I said, operations, science operations, we expect to start around 2026, 2027. So that will come a couple of years later. Yeah.
Okay.
Monica?
You mentioned that Australia is currently joining only for La Silla Paranal, and that is still thinking about ELT. How would that affect the budget for ELT if they think for too long?
Well, it will really be very helpful for us if they could join soon. And actually, we are talking to them about this. As you know, there is an Australian university which is participating in GMT. But this is not regarded as a national participation in a way or another. So the community in Australia, as far as I can tell, and when I talk to them, they're all very excited about becoming full members of ESO, to join also the EELT, but ALMA. There's also a very lively radio community in Perth and in this part, which is of course very interested in SKA, which is a national priority, but they are also very interested in ALMA, and actually they are very good at getting bits and pieces of ALMA observing time, and to do lots of good science with it. So I really hope that we can convince them to join ESO relatively soon, before the 10-year partnership expires. And that, as I said, it would help us a lot.
I was wondering whether you can tell us something about the next generation of VLT instruments, next generation.
The VLT?
Right.
Yes. So we have started a process called VLT 2030. There was a workshop in June where we had basically the instrument builders there explaining what their plans would be, what they would be able to build. That was actually very good. We have identified a few instruments, and there was also a little bit of a discussion on what we should do with the VLT in 2030, and there was rather a consensual view that we should exploit what it is unique for the VLT, the interferometer, but also having facility instruments that serve a lot of science goals. And we have workhorse instruments, we have a few of them. We should try to make sure that there's always a few of those. Now there's a second step into this, which is a community consultation. I mean, we are setting up a science prioritization exercise where we will be pulling the community for the science drivers rather than the instrument builders for what they can do. And we hope that during the next year we should be able to put the two pieces together with our committees, with the STC in particular, and come up with a plan. We do have a budget line reserved for instrumentation for the VLT. It's not very big, but it is there. I mean, and I would like to keep it as much as possible, because it is the insurance that the VLT will remain competitive. Even when the EELT is up and running, getting 2 hours of observation with the EELT will be a challenge. And I mean, I think that closing or leaving the VLT behind would not be a very good strategy. So we need to make sure that the VLT will remain competitive, at least with the horizon of 2030. So this is the process that we're following. And for some we're going too slow, for others we're going too fast, which means that we're probably right.
Okay, 2 actually. Elena? Correct.
I was wondering if the uprising in Chile might be a problem with the EELT, or is the agreement with the government already sealed, and whatever happens, you're fine?
So, formally speaking, we're fine. We have signed everything with the government a long time ago. The government is very fond of having us there, but of course the facts have shown that the government are not the only ones that matter there and anywhere else in the world. So when the uprising started on the 18th of October, I was there, and the first 10 to 15 days were very tough. We had lots of logistic problems. We had, of course, first thing we did was to send everyone home, or almost everyone. Of course, we had to keep our critical teams in the observatories. That was appreciated, and we were with very low staff numbers in the observatories for 2-3 weeks. Still, we observed every night, but okay. Then when the situation more or less went not back to normal, because it's not back to normal, when the situation got calmer and the logistics were more or less under control, we restaffed the sites and we're now what I would call into normal operation. But of course, I cannot predict what's going to come next. In Chile, there's at the moment a combination of two things. One is a very strong social demand of changing the economic model, making it more social, more like the one that we have in most of the ESO member states in Europe. And on top of this, there's these violent acts riding on top that are disturbing everyone. So I hope that the Parliament and the political forces take note of the first part of it, and they develop together with the people a new social model. I think it will be good for everyone. Now, I'm not sure how this will end up affecting us. I'm really not. I think we're okay. We need to work there not only with the government, but with the people, with everyone, to make sure that we all understand that ESO is good for Chile and that Chile is good for ESO. And this is something a bit delicate, but I'm rather positive about the long-term future in our relationship with the country. Sorry, you see that I'm navigating with a lot of difficulty in the political arena, but okay.
So, a poll among the ESO users a few years ago suggested that the community is interested in wide field and a high multiplexing spectrograph. There has been also a report by Richard Ellis and a working group in 2017.
Yeah.
So I would like to know if there is any plan to follow this interest from the community or to join other projects that in the meanwhile are ongoing, like the Mauna Kea Spectroscopic Explorer.
The short answer is no. And the reason is not lack of interest. The reason is lack of resources. So we, building the ELT, it's already a big stretch for ESO. We are in a very difficult financial situation because we are building a very big machine. And not only that, I mean, our people are fully committed to do this, and they are busy all the time with the ELT. In fact, we're now recruiting significant amounts of people. Last year, during 2019, and in 2020, we will need to find more people because we simply don't have enough to deliver the ELT. But delivering the ELT means that we have had to commit the resources of the organization very far into the future. So it means that, in practice, if the finances do not change, we will not be able to make a serious start into a new project, before the mid-2030s. So MSc is nice, everything is nice. There's also a lot of push from the radio community to have a big submillimetre dish, which is also a very interesting project. There's plenty of interesting ideas to develop. We simply cannot do them. I mean, this is as clear as that.
Okay. Very last question. Okay, so if not, let me thank Xavier for this very interesting talk.